Our next speaker is Aadil Oufkir, and he's going to talk about functional certifications and computer studies.
Thanks for the introduction. Thank you for this workshop. Today we'll be talking about quantum channel certification and incoherent strategies. This is a joint work with Amar, Nicola, and Tuebingen. The problem of quantum channel certification is about testing whether a channel behaves as intended. And this is an important problem because first, the building blocks for quantum computation are unitary gates. And so it is important to test whether the unitary gates are working well in order to succeed in our quantum computation. Second, the quantum channel certification is the natural generalization of quantum state certification. Since if the channel has no input, then testing such channel is equivalent to testing corresponding quantum state. And finally, the problem of quantum process tomography, which is the problem of learning a channel in the unknown, is costly, and it requires the NGO time value over epsilon square copies. And our hope is to reduce this complexity for the problem of quantum certification. So to formulate the problem of quantum channel certification, we have n copies of an unknown quantum channel. This is a CPTP knot, which sends the n-dimensional quantum states to the out-dimensional quantum states. These are given as a black box, and we are given a known quantum channel n0. And the task is to distinguish between the null hypothesis where n is equal to n0 and the alternate hypothesis where n is epsilon far from n0 for some distance with high probability. So which means that if n is equal to n0, we want that the algorithm output the null hypothesis with a probability at least 2/3, and if n is epsilon far from n0, the algorithm should output the alternate hypothesis with a probability at least 2/3. So for the distance, we choose to natural distances, the TS and diamond distances, because they have a nice rational interpretation. And in this talk, we focus only on the trace distance. So this is defined as the maximum over input state of the one known between the output states of n and n0. So the goal is to, of course, distinguish between the two hypotheses while minimizing the complexity which is given by the total number of channels. So this complexity, of course, depends on the access model, how we extract classical information from the quantum channels, as well as the certified channel n0. For some channels, some channels are simpler to test than others, as we will see later. So first, for the access model, we focus only on the incoherent access, which means that only one black box quantum channel can be used before a measurement. Concretely here, at each step T, the test algorithm chooses the dimension of the auxiliary system. Then the input state for dimension dn times dn, a measurement QVM of dimension dn times d-out. The input state is sent through the channel identity tensor n, and the output state is measured with QVM nt. So here we observe xt, which follows the probability distribution given by volume. And this is repeated n times. And we call the algorithm adaptive if we choose the auxiliary dimension and the input state and measurement group can become in the previous observations. Otherwise, it is not adaptive. So this is the access model. And the certified channel n0 will focus only on two extreme cases. The first one is given by a fixed unitary channel, which sends an input state to U over where U is the unitary matrix. This is the first extreme because it has a channel of 1. And the other extreme is the deployed channel, which sends in every input state to the maximum state. And it has a channel the in and the out. First, for certifying a unitary, fixed unitary quantum channel. So So here, note that the input dimension and the output dimension are equal. Note that by P. So we can characterize the optimal copy complexity in the non-adaptive setting with and without authority systems. This is given by order D over epsilon square. Observe that the upper bound is achieved by non-adaptive ancillary algorithm, whereas the lower bound applies even for adaptive ancillary algorithms. Next, if you want to certify whether a channel is a deployment channel or transformant, we can characterize the optimal complexity after algorithm factor in the non-adaptive system. This is given by order V in squared and V out to the 1.5 over epsilon squared. And here again, the algorithm is achieved by the upper bound is achieved by an ancillary algorithm, and the lower bound applies for even ancillary assist algorithm. Finally, in the adaptive setting, we can only provide a neutral lower bound, and the gap is at most squared. I would like to emphasize that here we show that auxiliary systems don't have this type of problems, even though we know that they have to improve the topic complexity for other quantum testing and other problems.
Could you say something about the e to the power 1.5? Where is that coming from?
Yes, here, for example, if D is 1, so we are testing whether the state of the channel is constant, the state is maximally next or epsilon r. This is testing the external problem. And we will try to cover this D to the power 1.5 or epsilon squared complexity. Where it comes from, so classically this is testing uniform, we have the square of D over epsilon squared. Quantumly, if we choose, I think this is optimal measurement, are unitary. You see that's one of the basis. We measure this states, and the TB distance becomes the epsilon, new parameter becomes epsilon over square root d out. And so this is why we have another d out. Yes, I think it's a good observation. So here the input and the output is different because for tomography or linear quantum channel have the complexity d in q times out. So we don't have this relation for the input. In the remainder of this talk, I will give some details for this class. First, for the fixed unitary channel, to recap that we can propose incoherent non-adaptive ancillary algorithm to certify whether a channel is fixed unitary, and the complexity is d over epsilon. First, we can remark that since the trace distance is entirely invariant and that is nice property of the trace, we can reduce the problem to the case where U is identity and N is channel. So now we are testing whether a channel is identity or epsilon. Maybe the first approach for this problem is to reduce it to state, and we have a natural combination which is the choice state, because it encodes everything about the channel. Under the new hypothesis, the choice state is the maximally internal state, and so it is natural to measure with the Tuebingen with the projector psi and the optimal projector. We will observe always 0 if the channel is identity, and so we can answer the hypothesis if we always observe 0. Otherwise, we answer H1. The error probability here will be given by trace choice state time maximum time state, and so we need to upper bound this error probability away from 1, and for this we can move an inequality. So we can upper bound this error probability by 1 minus the trace distance squared. So this is upper bounded by 1 minus epsilon squared over 40, and so now it's same to see that if we repeat this d over epsilon squared, we can reduce the error probability to nothing. So this is good, but we need ancillary to prepare the choice. And we don't want to use a zero system because here we are testing identity. So we don't want to use a perfect auxiliary system. One way to avoid this auxiliary system is to remark that this error probability is nothing but the internal fidelity. And we know that the internal fidelity can be related to the average fidelity. And here, in this average fidelity, we don't have auxiliary system. So you can use input set on the children, and similarly to corresponding to this order phi. And under the new hypothesis, there is no error. Under the alternative hypothesis, no error is given by the average fidelity. So you relate this average fidelity to the internal fidelity, and we have a similar upper and only p plus 1 and 0. So you can repeat this p over 2 square times. The upper bound is very simple, but this bound is not seems to be optimal if we look to the classical set. Because classically, if you want to test whether a classical channel is the identity channel or epsilon far in the worst case to the distance, the complexity is of order d over epsilon. And here we have epsilon square. And it turns out that quantumly this is optimal, and we can prove this much in lower bound, even for adaptive and syntactic parameters. So to prove, so before that, so yes, so this is the general strategy. So this is ancillary, so we can use ancillary each time, and this is adaptive, so every time you can choose the input set and the measurement device and the auxiliary dimension of the auxiliary system defining the previous those equations. This is of course stronger than more adaptive ancillary. So to prove the lower bound, the standard strategy is to construct hypertext channels. So here under the new hypothesis, we have no choice. The channel should be identity, but under the alternative hypothesis, we have a lot of choices. Maybe the first naive choice is to check channel that is the identity with hypothesis or 1 minus epsilon, and we add some noise in power epsilon. And this also can be, for instance, this perfection, but this can only imply lower bound of 1 over epsilon. And first, to improve this epsilon to epsilon square, we need to go beyond the classical, because we know that classical is d over epsilon. And so here we choose to make a rotation instead of perfection. And it works, it gives us 1 over epsilon square, but we want this dependence in the dimension. So here the basis is known. This is why we don't have this dependency in the dimension. And the first idea is to hide the basis by conjugation with a partition between 100 matrix. But we are only able to achieve lower bound of square root d over epsilon square with such construction. And the next idea is to get inspiration from the quantum speed levels and add, check the mixture with of identity and the previous channel. And now it works, we can achieve both optimal dependency in D and S. The rest of the proof is too technical and relies on the data. Here we skip it. So now to test whether a channel is horizontal channel or epsilon far. So we can propose an incoherent adaptive ancillary strategy, which has this complexity. So to understand this problem, we can rewrite the alternative for this. So here, test distance is at least epsilon, so which means that there is some phi, so that the output state n of phi is epsilon far from the maximum mixed state in the one. And this is very similar to testing this problem. The only issue is that we don't know this. Maybe the first naive approach is to make a brute force search for phi, but it's costly. The second naive approach is to go to the choice set and suppose that we can use ancillary. Then we need to lower bound the choice, the one between the choice set of the channel and the choice set of the origin channel, which is the maximum mix state. We have this equality between one norm and the other norm, and this the factor cannot be removed in general. So we can use this, and then we can use the result of sequence chain average. So which says that we can do test mixedness with the complexity d to the power 1.5 over some square. But now d is the dimension of the choice set. This is d in time d out. And the new precision parameter is epsilon over d. This is this complexity d in the power 2.5 times d out to the power 1.5 over some square, which is suboptimal as you see. So to overcome this difficulty, we can get explanation from the previous problem. When we don't know this maximizing state, we can choose it. Now we choose phi at random, and we want to control the distance between the image or the output state and phi and maximum mix state. So it's difficult to control the expectation of the one month. So here we will go to the 2 months square. Now we can compute this exactly. And it is roughly some constant time, the 2 norm squared between the choices. Then we need to write this 2 norm between the choices with the diamond of distance or trace distance. So we can prove easily this inequality, and then if we put everything together, we have the expectation of the 2 norm squared at least some epsilon squared over 2d squared times the out. Now we can apply another. We can apply another test in mixedness if we have such statement without expectation. Problem here is that this is the expectation, but let's suppose for now that we can remove this expectation, we have a similar quality. Then this is test in mixedness, but in the 2 norm. In this table, function B and O, we have such an optimal test in mixedness algorithm in the 2 norm. So in here it's only square with b over the square. Now the dimension is the out, because this is the dimension of the output state. And we don't choose the system. And the new precision parameter is epsilon over the square with the out. So if we put in the parameters, we obtain all the b square times the out, or 1.5 over epsilon square. This is better than the previous complexity, of course, and we don't need anything. Previously, we need an answer to prepare the choice. The only issue is how to remove this expectation. And it turns out that we can prove that we port at least 0.001. This random variable x is at least half of expectation. So this is not by a concentration result, because a concentration quality will not give us sufficient lower bound. And here we use instead a second moment approach, and we upper bound the variance of x by some constant multiplication of x squared. This is the most technical part of this upper bound. Then you can use the quality. This is for the upper bound. Now, we can do a matching lower bound after a working factor for non-adaptive NCSS algorithms. So here, the emphasize is only for non-adaptive. So we prove lower bound for this type of algorithms. We can use another system at each time, but the choices of the input state and the measurement devices and the dimension of the resistance should be fixed before starting the study. So the idea is the same to construct how to test channels. And under the new hypothesis, we have no choice, but the channel should be the origin channel. Under the alternate hypothesis, we have lots of choices. The channel should be at least epsilon far in the trace distance. And here we can sort by the origin channel and add some noise. So the first part of the noise is W, where W is a hard distribution unit structure. This is to hide this maximizing state. The second part of the noise is this matrix U of Gaussian entities. And this is to hide the best Tuebingen, the best observable to distinguish between H1 and H2. And here we are using Gaussian instead of hard measure, so that we can apply the hypercontractivity of polynomials Gaussian values. Of course, there is a lot of conditions here, so that this is a valid channel, and also for the analytics afterwards. There's key possible details here, and the portion you can do. So to sum up, so we can calculate the complexity of certifying an FX unitary channel. This is given by order V over epsilon square. So here adaptivity or other resistance won't help. And we can also factorize the optimal complexity for certifying the deployment channel in the non-adaptive setting, and you can do a weaker lower bound in the adaptive setting. The gap is at most square root the out. We have other results in determinism. We can look at this version. I would like to end with three interesting open questions. The first one is to close this gap between adaptive and non-adaptive strategies for this polarization. I conjecture here that adaptivity does not happen, so we only need to prove this lower bound for adaptive algorithms. The second one is about instance optimality, and here the goal is to show that, to prove that the optimal complexity for certifying a channel N0 can be written as F over epsilon square, where F depends on the known channel N0 and the input and output dimensions. I should mention that this was proven for discrete distributions like variant and variant, and some results are proven for state certification by changing and coding. And finally, we know that coherent strategies where one is allowed to use these black boxes in parallel can outperform incoherent ones for state certification, and we got square root d. So here it is interesting to ask the same question. So can coherent strategies improve the sample complexity of incoherent ones for the problem of certifying chain? That's all I would like to. Thank you for your attention. Any questions?
Why didn't you do it in base systems and not diamond? Because I mean, you
We
have
have
both
both.
essential systems, right? So I mean,
We have both.
oh,
I have chosen to only present the systems.
Oh.
Not overload the presentation, but we have both.
but it's more complicated.
Actually, for the lower bounds, usually we have this same construction in the test distance, which works for the limit distance because the limit distance is at least the test distance. I think the only difference will be here to certify whether our channel is fixed unitary channel. For diamond distance, we have only ordered the over epsilon square, and this may be suboptimal. Any questions?
Can these ideas be extended to cases in between rather than extreme cases?
This is a big goal. This is instance optimality. We want for each channel and zero made this. So here we somehow we have found for this complexity for the islands in each channel, and given some results for the deployment. Why deployment? Because for example, for tests and discrete distributions, to extend the result to every fixed quality distribution, we use this testing uniform as a separation. And maybe this can be used channel as well. And yes, this is the bigger one.
So for the instance of tomorrow result, do you have a sense of what would be the right thing? The running back result is like that weird, like 2/3 was which is not exactly like the camera. And that's not the calculation. In the case of the right notion.
So in this paper of Shannon and Owen, provided a lower upper bounds. Remember that this is something like 2/5 norm of the set sigma 0. Yes, maybe not maybe it can be some norm of the channel at 0, maybe the joiner or
No, that's the thing. Okay.